Hi everyone, I'm Jyoti Chakraborty. In this video, I will briefly explain my answers for the four questions from the second round task from DataSynthis. So the question one, given an AVL tree storing numeric values, design an algorithm to efficiently return the sum of all values within a given range, left and right. So for the AVL tree, I added a new field called subtree sum to each node so that every node knows the total of all values in its subtree. During insertion or rotation, this value gets updated. Then, when we query at range left and right, that particular range, we only visit the branches that overlap that range, giving an efficient of analog and time. So about the follow-up question, uh, for updates that need to send changes to machine learning models, each update can simply propagate small deltas through a feature store or event stream. The models stay in sync in real time. If I show the code, that is the implementation of the logic. So the sum in range 6 and 15 will be 45. Now coming back to question number 2. Suppose you must store and retrieve large model weight files distributed across a database. Explain how a B-tree supports fast search and insert operations at scale. To answer question number 2, a B-tree keeps data balanced and stored in blocks, which makes searching and inserting large files fast. For model weight files, we can split them into chunks and store them using a B-tree index for quick lookups. For the follow-up question, like how this applies to feature vector lookups in recommender system. So in recommender system, this idea helps locate user or item feature vectors efficiently using key-based lookups, while vector similarity itself is handled by separate and indexes. Now, question number 3, outline an algorithm for finding a minimum spanning tree, MST, in a distributed system. So for finding a minimum spanning tree in a distributed system, we can use algorithms like Profgra or the GHS algorithm. This allows each node or worker to find its local minimum age and then merge results, which fits well in a MapReduce or parallel setup. And the detailed explanations are right given here. The examples of distributed algorithms, which is MapReduce family outline. So about the follow-up question, ML real-world scenarios using MSTs. So in ML, MSTs can be used in sensor network optimization, feature selection, or even hierarchical clustering. Now coming to the question number 4. For a tree or graph-based feature index in a memory-constrained environment, compare slab allocation versus garbage collection as memory management studies. So to compare it, in memory-limited systems, slab allocation and garbage collection are two memory studies. Slab collection is faster and predictable because it pre-allocates fixed-size blocks, while garbage collection is easier to code but can pause unpredictably. Another thing is garbage collection (GC), automatic memory reclamation that identifies live objects via tracing and reclaims unreachable memory. So it provides programmer convenience but can introduce pauses or extra CPU time for GC cycle. And coming to the follow-up question, which option better supports predictable latency for online serving in ML systems? So, in my opinion, I will say that for real-time ML serving, slab allocation is usually better since it gives consistent low latency. Thank you for watching.